If technology is the driving force of innovation, then accelerated computing and extreme data are the gateways to world-class innovation. In an exascale era, the scope of our capabilities grows exponentially.
We are collaborative. Research is the catalyst of science that inspires the exploration and understanding of the unknown. Our interdisciplinary approach and partnerships redefine the boundaries of what digitalization can achieve. We're not just simulating the future, we're leading it.
We are open. In an interdisciplinary world with multiple ecosystems, we champion open models, transparency, and knowledge sharing. We set the benchmark for trust and ethics to create a culture of knowledge generation that's accessible to all.
We are transformative. We are constantly looking for sustainable ways to positively impact society. Science, research, innovation, education. These are our tools to empower human development.
We are innovative,
Collaborative,
open.
transformative.
We are Alps.
Good. With this, I would like to ask Claus and our panelists, please, to the front. I think this will connect nicely between what we've seen in the science talks before, and was already mentioned, and the impact that a system and a research infrastructure like Alps can have on society.
Yeah, thank you. We have seen exciting examples of research that is made possible by the Alps infrastructure. The aim of this panel discussion is to bring the speakers together and to reflect upon the changes, the transformation that are sort of announced, also to have a critical eye on it. I'm a philosopher, so Socrates asked these silly questions, and I'm trying to get speakers engaged by asking some kind of questions. So let's start with the transformative aspects of the Alps. And I think one aspect is just science. We'll later talk about society. And we have been talking about a new era of prediction, a new scientific revolution, something like that. So in brief, I mean, what's really happening here? What's the impact of high-performance computing on science? Do we see a new revolution? Tanya, maybe I start with you.
I would say rather than a revolution, say, in science, I would more say a revolution of how we work as scientists. And that could be as scientists, I mean, we do also a lot of non-science work. And there, I guess we saw from Torsten, pictures are generated with AI. I like to, make bullet points and create text, etc. So all those things around what is not the core science, I think it helps us immensely, and it revolutionizes, like, a couple decades ago when we had computers helping us. And then going to the core science, no, I think we are the ones deciding which questions do we want to ask. What is important to advance society, to advance research? So we need to phrase the questions, collect appropriate data which actually contains information to answer the questions. And then, of course, the whole AI comes in analyzing this data. But then also at the end, how we interpret that, how we put it in context with our hypothesis, that's again us, the scientists. I think the bit of analyzing data, yes, but not a science per se.
What do you think, Peter? Do you agree with that?
It's different for us, I believe. I think as I said, we have experience with HPC, and more is always better. Having a bigger machine, great. But what changed really, I think, is the aspect of machine learning. That ideally you have a machine that can do both. 64-bit crunching of numerical equation solvers and 16-bit machine learning training and inference. At the same time, what I think one big change is this what's supported by vCluster is the idea of it's not so much the focus on a single machine in a single country anymore, but you have to see this as a component in a larger federation of HPC and data. And what can you do that allows you actually to scale this up? And it's not just the limit of CSCS anymore. It's everything that we have available if we put it together intelligently. And I think then we are in a totally different space.
You're also doing very applied stuff, and what's your view on the change, the significance of these revolutions on science?
I guess the question is more about like what is a revolution, right? What classifies, what level do you have to get to when it's revolutionary? And in medicine, I suppose we've got several examples that really changed the game, and like not just changed clinical practice, but changed like the amount of people that didn't have to die from preventable deaths. So like, let's say like antibiotics and vaccines or chemotherapy, insulin, these kinds of things, right? And while these are like really revolutionary discoveries in science, the thing that makes them complicated is they develop like a huge amount of data to actually understand and incorporate them into useful insights. And on top of that, all of those things may be very revolutionary, but for who? The vast majority of society doesn't actually have access to them. So what data science can do, especially at large scales, can do two things. It can understand the complexity of data that we are generating from these more complex revolutionary discoveries that we're making. And it can have access to those revolutionary discoveries. But also, it's allowing us to predict things for all the places that don't have access to them at all. And I think that can be revolutionary, to increase access to things that are revolutionary through data, through prediction, and through implementing them at scale. So yeah, I really believe in that this is a kind of a transformative moment in medicine, at least.
So it's not so much about the real science, but rather about the implementation. But I mean, let me read something to you.
But there's implementation science. I've got to plant my flag here. Implementation is science, and there's a science in implementation. I'll be provocative.
I mean, let me read something to you. There's a science journalist called Chris Anderson, and he has quite provocative claims about the future of science. So he's writing that correlation supersedes causation. Science can advance even without coherent models, unified theories, or really any mechanistic explanation at all. So, I mean, this would really be a new kind of science. And my question is, do you see this on the verge? Do you think this is coming, or is this an over-exaggeration? Maybe, Nicola, you have a view on that.
So I mentioned earlier in material science, we do start to use now machine learning models in combination with high-performance computing to try to design and discover new materials. And there you could say, well, the machine is kind of just looking for correlations, and it can do that without any understanding. I think the jury's still out about whether this is successful or not. And I think if a machine does make a prediction that turns out to be a useful one, of course, as scientists, we would go back and understand how it got to that answer, and also what are the properties of the material that makes it so useful. So I see this, it's kind of a non-statement in the sense this is another tool that might help us think come up with new ideas or think in different ways. Because a machine, of course, is much better at seeing correlations than a human, because it has access to much more data, seeing and analyzing correlations.
Jean-Paul, would you agree with that? What's your perspective from cosmology?
Yeah, I guess, I mean, computing is giving us the power of going beyond what we can do today. Because, we're kind of limiting with dealing with the data, and whether that we have those computer available in coming and in future, we will be very limiting in understanding our universe. So I think this effectively bringing us the possibility to discover new things, which was not possible before. So this is really revolutionary.
But I mean, this mechanistic understanding, is it still an issue? Also, Peter, I mean, you were talking about the ML models that are better, and then these computer simulations that are based upon physical equations. So, I mean, is this the future, a pure data-based science, and you get better predictions than with theories?
I'm not sure about that. I think it's all in our control, isn't it? I mean, we want to understand the science, the first principles of science always. Even if a machine learning model does something better, we want to understand why. Because maybe it's an artifact and it only does it once and not the other million times we depend on it. But it's in our control, I think. It's the way we construct them, what we train them with, what we compare them with, But I think it can help us a lot, as was said before. It's very clever at dealing with a lot of data. which is otherwise not possible. It helps us reveal correlations that we haven't seen before, but then we have to make the extra effort to understand them. So it's in our hands, I think.
Interesting. Tanya, would you agree? I mean, in your field, you don't have these kind of big theories like in physics, so that your field might be better suited to this pure data approach. What do you think?
Well, I think indeed we don't have as many equations describing, I don't know, starting with Newton's law in biology, there's much less in life sciences. What I do think, I mean, all those big data sets, there is this opportunity that we can now get or have hypothesis raising. We find correlations, but then I'm convinced every life scientist has to go back into the lab and determine, is this mutation actually really causing, you know, some functional or not functional phenotype, etc. So I do think to actually understand what's happening in the living world, we still need the experiments, and the data just accelerate. The data and the computing accelerates to raise hypotheses, already exclude certain kind of, you know, possibilities and focus on what seems to be plausible based on correlations.
Maybe something that is changing now is that different scientific disciplines come more together. I mean, you're using the same research infrastructure. I guess you're using similar methods. So, I mean, do you talk to each other? Can you learn from each other? Are the scientific disciplines sort of converging on the same type of thinking? Nicola, may I ask you?
I think it's always been the case that we learn from each other. We struggle to cross language barriers with people in other disciplines, and I'm not sure that there's been a paradigm shift in that with more data-driven methods, or it's just an ongoing process.
But machine learning is used everywhere, and I mean, it's the same kind of problems that people have. I mean, here you're working on very data-intensive observations, trying to supplement them with models. I mean, can't you talk to each other and learn from each other? You two?
We do now.
I guess there's also kind of an acceleration of, you know, interdisciplinary. I mean, to build these, you know, what I call the astro radio interferometry computing. I mean, you have to bring, you know, experts into different domain that, you know, were working before, but they really have to work together. So I think it's this acceleration that we are seeing.
Yeah, there's lots of common elements. I mean, we do interferometry, you know, so methods supporting that, making that more palatable or faster, you know, could be the same, identical almost. I think I see that LLMs is certainly something where we can learn from each other, how to make the output from LLMs trustworthy. You know, how we can drive what we train them with so they serve our domain in a trustable way and not just create stuff that, you know, we don't know where the sources are from. You know, how do we create that interactive layer with data that we can talk to, that was shown in several talks, how we can create that so that we can trust it as scientists supporting decision making, for example. That's very important, you know.
And what about the role of computer science? I mean, do you have computer scientists in your lab?
Yes.
Everywhere, basically? How many people from computer science do you have in your, what percentage is it?
From computational science, I would say, rather than from computer science.
Yeah. Okay. Yeah. So this is different. What's the difference?
So there are scientists using computers, I say.
Yeah.
So computational scientists.
But this is some kind of universal language then? I mean, you have scientists that are good at working with high performance computing and they can be used everywhere?
I could say that many of my PhD students who decide not to stay in research for sure end up as scientific programmers. So they have this tool, the tool that we use in our research is a skill that's certainly more widely applicable. I think that's the case for many of us in the computational sciences.
Yeah, I agree with you. I mean, lots of people, you know, who don't want to continue in astronomy, they basically go in computing science, data analysis, data management. I mean, we have so much data that we really are faced to, you know, to dealing with this data, and most of my PhD students, they are like keen and interested, and we bring them into also an environment where we have computing scientists, we interact with, you know, CSCS people, and they learn from that.
I'm happy that you're starting to talk about students, and I'm also very happy that I see some students here. So what does CSCS, the Alps Research Infrastructure, mean for teaching and education? Is it already part of the curriculum?
I guess it should be. And I guess in those disciplines that are represented here, it's essential that we deal with, supercomputing. Supercomputers are useful for, bringing new discovery. I mean, going beyond what's the current level. So if you're not involved somehow, you're missing something.
But I mean, are we doing well on that? I mean, is there enough supercomputing in the curriculum? Are students really prepared for the future?
Well, I mean, some of my physics, students who are interested in coming to my lab, at the end, usually they end up having classes in, not astrophysics, but computer science, because they have to catch up.
Yeah, that's interesting. Any experiences from you?
So I think certainly our research students are using supercomputers all the time. In the curriculum, perhaps what is more important are the methods rather than the platforms. When we're teaching the basics of computing methods, then the platform that it's run on is perhaps not so critical. They have the tools then to move to other platforms later. I think as educators, of course, in our undergraduates, we teach them all now machine learning methods, because otherwise it would be irresponsible of us, machine learning and material science. And as educators, we have, I think, opportunities and challenges posed by, for example, large language models. When we're setting assessments, we have to, if we want to test a skill of a student, we have to, of course, first check that the large language model isn't better at that skill. And we also ask ourselves, well, if ChatGPT can answer this problem, do we need our students to develop this skill? And so we're really rethinking what and how we teach our students, what skills they need in this emerging paradigm of knowledge.
It's a great challenge.
Yeah, it kind of merges some of the questions that you just asked previously as well. Like, if you think that like computation is getting so complex that it's just going to overtake the scientific process, then what do you teach students in science, right? And I think that I disagree with the statement, because it's a misunderstanding of what science is, right? Science is about understanding things. It's a human exploit. Why do we write papers? We write it so that we can understand science. So even if you've got extremely complex things, we mustn't mix up signal and noise, right? Extremely complex correlations that underlie some observation. It's up to us to decide what's interesting. And that's science. It's about finding things that are interesting to us so that we can extrapolate from that and explain them. And I think that is what students nowadays need to kind of appreciate, that they're not being replaced, that we can just have more signals that we can learn from. And it matches with the other kind of topic that you had before on this interdisciplinarity, because right now, especially in implementation science, you're dealing with so many different people, and we actually have a project just dedicated to a semantic mapping between our humanitarian actors and how we are doing AI. And this is with the ICRC. So the International Committee of the Red Cross, they don't do data science, right? But they do humanitarian values. They are custodians of these values. And how can we make our models actually be principled with humanitarian values? And there are ways that we can do these mappings and make a kind of an intentional effort to do that. And I think that these are the kinds of skills that are quite interesting right now to teach our students, this interdisciplinarity and an appreciation of how we can better use the signals that are being generated by these models. Yeah.
And has this been implemented in the curricula? Are we good at that? Or do you think we have to change our curricula to make students better at that?
I really think that there needs to be more. I mean, that's ad nauseum now. I'm saying this so often, but implementation is really something that we need to start thinking about more seriously, because more interdisciplinary skills set is needed now. There's a lot of people that are making tools, and there's some horrible statistics about how many tools are being made in medicine, for example, and published, and then just abandoned. There's so few that are actually being tested in the real world. And I think that that's really something that humans are pretty good at. We're pretty good at being in the real world, because we kind of are, right? So it's like a human exploit of just embrace the real world and implement the tools that you're making. Yeah.
Getting back to students, I'm wondering about their job perspectives. I mean, if they work with these infrastructures, is this good for their perspectives? Do they find jobs in industry, business firms, elsewhere in research?
unfortunately, they go to industry too often. They're like, I have to lure them. It would be very nice if we could offer them higher salaries. So because we can't, we have to really offer them meaning, right? Okay. And I think that's really important. And to lure them away from these high-paying jobs, you really have to give them something that they can be proud about. And that's the tension, to lure them away from these like hedge funds and all that kind of stuff. It's tough, but it's true that industry has normally got all of the high performance computing. It was always considered to be the place where you can have the most fun if you're a machine learning scientist. And now, when we have access to this, people are like, don't care about Meta. I want to work here because I've got the integrity, I've got the impact, and I've got all the fun of the computing. So I think it really is important that this is accessible to young students so that in the beginning of their career, which as you saw on my slides, like the person leading all of our technical stuff, he's a first-year master student.
That was fascinating.
Yeah, and it's the whole team, you know. So I think it's really important to expose them young so that you can, they have time to shape their careers while they're busy learning.
How's in your field, Tanya? You're nodding.
Yeah, I mean, I would fully agree. And I was just thinking also on top comes the open part, because, I mean, of course, all my students, I mean, we work in life science, but it's all statistical tools. Doesn't need to be now classic machine learning, can be very different statistics, but you can use that anywhere where there's data, so they have no problems finding jobs. I think what they find very appealing is if there's this opportunity to do something openly where you can share with the world, which, yeah, if you use apps, you can talk about what you're doing, while if you're at Meta, you may not. So I think this maybe is also something kind of weighing out a bit the salary difference, because that's a real thing. I mean, they could leave before finishing their PhD and, you know, get rich.
Yeah. I'm happy you're talking about openness, transparency. I mean, we have seen open is one of the properties of the Alps. So what can CSCS contribute to open science? What do you think can we make to make a difference here, to make science more transparent to the broader public? Can the Alps infrastructure and CSCS help here?
Yeah, so I think generally already, so I mean, one can do all this exciting science, but then also thus far the big kind of, you know, machine learning tools say, look at OpenAI, even though it says open, it's a closed system. And there's been a lot of talks about also risks of those systems, and only if we have open academic environments where we can investigate such tools, we can actually identify risks, but also potentially identify opportunities for all of society, which, and the companies have different aims, not for the better or worse, but so I think there's a real argument to be made that this niche needs to be also covered by academia and open.
Yeah, and academia is so unique in that way, right? We're neutral. So I really appreciate that as well. And we that's something that only we can really offer. And it's important that we then are also like owners of this open platform. But open source is one thing. I mean, I can go make a model, which we are going to make a model, 405 billion parameter model, and then we open source it. What does that mean? Who's actually going to use it?
Yeah,
it's a set of numbers, right? Who can actually use it? Who can actually host that model? Even our 70 billion parameter model right now, it's $4,000 a month to host it on a standard cloud, just to ask it questions. So open source, it's technically closed because it is unusable. And so I think this, like, again, going back always to implementation, I guess it's my drum that I'm beating today, but it's about if it's not really accessible in terms of like just being hosted for inference, for example, so what can ALPS do? Can certainly invest as well in inference hosting, having a few nodes at least so that people can, it's open in terms of people being able to use it, but also to be able to reproduce its claims, to be able to do benchmarking and evaluations. And that's when it's open, when people can actually access it to probe it as well. So open source is one thing, but we need to realize that not everyone can launch it locally to use it.
No, I completely agree. I mean, these machine learning models are opaque, and I mean, there are tons of data. So normal users cannot use them. But what can we do about them? Because, I mean, there's the stream of transparent science. I mean, science that is open to the interest of everyone. Everyone can validate scientific claims. I mean, that would be great. But what can we do? And I think this is a real question for CSCS, because this is a big institution and they can think about how data can be made available really, or accessible to people, really accessible. I mean, do you have any ideas about that?
Well, maybe I would like to, put something here. I mean, when we talk about cosmology and cosmological data, we have a community which is worldwide. And as I mentioned, we're going to be swamped with data. And so we need the help of CSCS, but we need also to have the help of or what we call the SK regional centers that will be distributed all over the world. But here, CSS is interesting because they have this openness and they're working with other computing centers, in Australia in particular, and they're leading the way. So I think the initiative here in Switzerland is very good because it could be also taken by other supercomputer centers and making everyone trying to work together. And I think this then could be also a legacy for other science globally. And I think that's my pinch here.
I can't help but also just comment on the data part because, it's in healthcare at least and also in humanitarian response. I mean, some data we can't just get, well, be open and put your data out there because, of course, it's patient data. And you can't say, oh, well, it's anonymized because anonymization is a topic that just degrades over time as our computing abilities become better and better and we can re-identify it. So you can't just share data, but you can share its insights, right? And I think that's what we're doing, at least. We have a platform called DISCO for Distributed Collaborative Learning. Of course, it has a slowly rotating disco ball as a logo. but this is, it's important as well to kind of recognize that federated learning and insights from data. So in other words, building a model together collaboratively, but without sharing the data is also open, right? But it's just also respectful of the privacy concerns of the data. So, and not only privacy concerns, because that's one thing that's really important in medicine, for example, but it's also ownership. And I think it's very unfair that, that places that have got lower resources have to give up their ownership to a higher resource setting. And that's what's been termed as data colonialization. So we do have to have some structural methods to fight against that and to protect local ownership, but still sharing the insights of the data and building things collaboratively together. Yeah.
Mm-hmm. And maybe transparent is there a good word, because indeed not everything can, for ethical reasons, potentially be shared, or we cannot rerun and retrain every big model. I mean, then also I think there's a bit of a problem with the energy. But being transparent, what are the processes, what has been done? And I think in other fields that's also something normal. Just in computer science, thus far we could rerun everything in principle, etc. But say in life sciences, currently this avian influenza infecting cows, they do experiments in BSL-3 labs with cows, but there are 3 such labs in the world. It's super expensive, so it's pretty much done in one lab. I think it's useful research. It's not really reproducible because you just can't do it here. But if it's transparent what they've been doing and following protocols, we can all learn something from it. And I think we also move a bit here that not everybody can rerun everything.
Yeah. I mean, this is a matter of data documentation, metadata, but this is something that researchers can read, but not people that don't have a scientific background. I mean, I liked your example, Tanya, with this chatbot that was translating queries into SQL. And so maybe machine learning can be used to work on these kind of data, and then people can at least sort of ask questions about the data. Would that be an option? I'm just trying to develop that further. So that, they can do something about the data and they get accustomed maybe to them, they can ask questions, and so it gets a bit more transparent to them.
Yes, indeed, but I think there's also always the question which data is intended for the general public to learn something about and which data is intended for, say, the specialized research community to learn something about. And yes, during a pandemic, probably for everyone, it's interesting how some variant is spreading. But during other times, I would argue some of the data I was talking about, I mean, you don't necessarily need to look into it because it's not, unless you're just generally curious about this data. So I guess we also have to think about which data is for which use case and for which target group.
That's right. But still, I mean, the ideal of transparency and openness would require that scientists are at least sort of transparent on which data they take. Because, I mean, there's a selection going on there. We have more data about the global north and the global south and so on. And I think that has to be made transparent.
And privacy is not necessarily in conflict with transparency.
Yeah.
That's just, it's something that we can resolve. It's not like they don't go hand in hand. You can be transparent and still retain ownership and privacy with technology. Yeah.
Moving to a slightly different topic, internationalization is something that we've heard about. I mean, there was this joke about the Alps. Where exactly are we going? It's Swiss, but also international, European. So in terms of internationalization, what exactly is the status here, and how might CSCS and the Alps research infrastructure help us to become more international?
To me, I tried to show this in this one slide where I said, like, we have this pie chart, and this is where CSC could sit, CSCS could sit, but also other centers. So we are in the fortunate role, I would say, where we actually have achieved already a high degree of internationalization. And that's operational, so for research anyway, but for operational, which means like everyday time-critical production according to standards and open data. So we're in a slightly better position here, but there may be additional difficulties once we enter private space as well, but let's this aside for a moment. So to me, CSCS is a great step towards a new level of internationalization. So we had connectivity before, and we exchanged data before. But if you really think about this, if you want to really go towards unlimited resources of compute and data and make it accessible for people without having to move any of it, really, there I think CSCS is really leading in what they're trying to implement. So with the links, the data links they have, but also the computing platforms dedicated to data. Where it's not about creating the data in the first place, but dealing with the data that you have produced in the first place. And your 600 petabytes per data, you don't want to move that anywhere. You want to give people access to it, and that they can take out what they want with fast methods. And that's what CSS I think has leadership over actually right now. And to me, this is an entirely new degree of internationalization, apart from contracts and exchanging a bit of HPC and stuff. So this is a new level.
Now, climate science is quite special because, it has global data. It's very different in material science, I suppose, because you can obtain your own data at home.
But I'd still say that science is fundamentally an international enterprise. Fundamental research, it's really hard, right? If it was easy, it would already have been solved. And so we need we need the best minds from all over the world to work on these really difficult problems. We need diverse teams of diversity with many genders, with many backgrounds, ethnic backgrounds, and nationalities. And without that, we don't make progress. And it's actually been, I'd say, catastrophic for us in Switzerland, our exclusion from Horizon Europe over the last years, both for the Swiss and for the Europeans, that our collaborations, our ability to collaborate smoothly was hindered by that. And having world-class international institutions like CSCS and the Paul Scherrer Institute based in Switzerland is really essential, so that people will at least still come to us while we're in these isolationist periods. So it's really essential.
But what concretely is the role that CSCS can play here? Does it compensate for the fact that we weren't part of Horizon somewhere? Does it spur more collaborations between...
Collaborations, I think, collaborations.
And Switzerland is international. Like it's the seat of WHO, of all these massive international organizations. For me, it's the DNA of Switzerland. It's the neutral space that where people come to negotiate from around the world. It is international. And what a shame when you have this massive computing center that you would only look at the tiny fraction of geography, for instance. And that's not what you guys are doing. It's clear. The vision is bigger because it's so big. It expands beyond that. And so, CSCS, just to follow the DNA of Switzerland, is to be international and to have that kind of impact, because there's nothing more valuable. It's also smart to do it, right? Because if you show that you are useful and you're doing useful things and you're doing it at scale, people want to invest in that. And I think that internationalization, it's globalization. Everyone is the world is very small at this point. So I think that it's clear that all the projects that are being done, I think, have an international flavor to them. They also are made better by international people. but international projects are much more impactful, right?
But what's the next step? I mean, we were kidding about the Alps and other mountains. And I mean, there is already this collaboration with some Scandinavian countries. I mean, if we go for the next step, I mean, that must be a scale larger than this center. Probably it will not be, I mean, located in Switzerland anymore, but more international.
It doesn't have to be. It can be anywhere. I mean, it needs to be affordable, of course, and green.
Yeah.
That's the number 1 and 2 requirements. And the only way, as Thomas showed, is probably somewhere up north. You know, but then, given the infrastructure that's being created right now, it doesn't matter where that sits. You know, and so we should move away from, you know, I want to cut the ribbon of the biggest computer in the world tomorrow. It doesn't matter. It's an important piece that has leadership in many aspects, as was shown. You know, and in the future that scales to other countries because you have all the right connections, and there you go.
Yeah, I mean, I agree. I mean, it doesn't depend on the location of the thing, right? But I mean, who can pay for that? I think in the next, when we get to the next level, it's probably not a single country anymore. I mean, we have to join forces with other countries, and we're doing that. Mm.
It probably needs more money, but I think it could also be more cost effective. Avoid duplication a bit better. As I said, we're quite okay organized here, but we still have, at least in Europe, no, in the world, I would say actually, the idea of, you know, you must own your own supercomputer, you know, must procure it and it's for yourself. There's some sovereignty and military aspects, but I think that can be sorted out actually. So I don't think it's a necessary condition for this. So you could be more cost effective in an international collaborative framework and save money.
And I would agree, money is one thing, but I think also when now starting to think even bigger, the other aspect one needs to think about is energy and the way we produce energy, and we don't do it in a sustainable way yet. And so, you know, increasing the CO2 footprint by margins for those infrastructures is probably not what we want either, to then have them calculate how we get to a more sustainable world. So I think the energy will be, for the supercomputing and many other societal problems, a huge challenge.
Yeah. You wanted to add something too?
No, I was going to say for sustainability, it comes back to the whole point of utility. Lots of places can be sustained by usefulness. And I just think that it comes back to that if you provide something that's measurable and that people want to be part of, you'll get buy-in. And that has sustained many NGOs around the world. So I think if this is kind of like that kind of organization that is being sustained by what it's producing, I think that would be wonderful. Not being sustained because it exists, but being sustained because people want to participate in the research. Yeah.
But yeah.
Just one more thing about this internationalization, and that's the public-private kind of thing, you know. So I think we need to be slightly more proactive with the link to private companies that again have access to other dimensions of computing and data. There's dangers as well, you know, technology, you know, you can be tied to a certain technology and not get out of it anymore. You may pay little at the beginning, but then a lot more later. But I think that can be managed, because if we can convince some of these technology companies, Peter, that there's a mission. It comes back to your point before, you know, if we can convince the students, yeah, you can make more money there, but here you can serve humanity, a society, you know, that you do something entirely different actually, and come to us, you know. And I think many of the companies actually have that on their posters already. But I think there's something to gain here if we're careful about how we do it. But we should not say, you know, we want to protect our public world because we don't believe in this staying open. I think there is some room for public-private engagement that gives us more and better, actually, for them as well. You know.
You have been talking about the costs in terms of money, in terms of CO2 emissions, and I mean, this is an issue. It's quite an investment. Switzerland was well positioned to make this investment. I think for Switzerland it was sort of cheap, but still, I mean, it took some money. So my last question to you is, I mean, how would you justify that to government, to people, sorry, if people ask you, I mean, on the street, I mean, how do you sort of defend this investment? Why can we afford it? Why should we do this?
This is not a question I see being raised in Switzerland. I think the Swiss population is intrigued by is in favor of fundamental research and the advancement of knowledge and an educated populace. I've never been I've never seen that question raised. It's rather a unique environment in that sense. I don't know what other people's experiences are.
I don't think it has to be a trade-off either. You know, it doesn't have to be, oh, we bought this supercomputing center and we're going to take away all of your healthcare or, you know,
I guess in Switzerland there's no trade-off.
Exactly.
We have that as well.
So here we are in a unique environment with that, but it's still, in a lot of places it is, right? Mm-hmm. And maybe that money could have been spent on something else that would have been very directly tangible with an impact in society. And I think if you do want to, and it comes back to my broken record thing, I suppose, but it's the whole thing that we can choose what we want to spend this on, and if we can actually make societal impact with the research that comes out of it, and if you make it intentional and you have a pathway to actually using it in society, then it's not a trade-off, and then you don't have that question occurring. Although, as I said, the question doesn't occur here. It's a very interesting observation, but it's true. Yeah, it's funny.
Although I would say in a more recent time with the financial situation generally of Switzerland, I mean, we're well off, but compared to a couple of years ago, I mean, also ETH has budget cuts. I think it's a lot, and it has been all the time going on, this explaining both the society as well as politicians, you know, what are the benefits, and potentially giving examples from the past, because often research is cutting edge, and yes, we have some vision how this can help society, but some things do help and others stay basic research, which is also fine. And say in our field, it was 20-some years ago, the Human Genome Project. So deciphering the whole 3 billion nucleotides I talked about, it was a multi-billion international effort. Now you get it for, you know, a meal in Zurich, a dinner. For that price, you can have your DNA. And actually, it helps if the medical doctor knows which mutations you have. You can potentially treat a disease better. So I think there's a lot of return, but you can only explain it retrospectively. Back then, it was 3 million for a few letters.
Still, that's more a comment on the disproportionate expense of Zurich meals, though. Yeah, but actually there is a trade-off, I suppose, that I have heard, which is people are actually getting quite upset about the amount of carbon footprint it's creating. So that is something that I do hear back. Like, and actually in our lab we monitor. So it's like just carbon-aware computing. So they monitor how much and give tangible results of like what they've done during a semester project or a master thesis. So just so that they can feel bad, right? And so it's literally doing that so that they feel bad enough so that they optimize their research processes and don't use too much. And sometimes they feel so bad. I had one student who planted a tree. So there you go. So there you go. Yeah, so just carbon-aware computing. But then people will ask about, like, well, is it worth it? And people have different values. Some people don't like, this kind of research, but like that kind of research. So I think you can't really win the game. Yeah.
Peter, what's your answer to the question of justifying this investment?
Look, for us, I guess, if I give a domain-specific answer, like weather and climate, I mean. We're talking about trillions of problems, so you don't want to pay for a computer, give you better handle information system to deal with it. So I think for us it's easier, yet not trivial. So why don't we have a 1 billion, a 10 times a machine like ALPS for climate, dedicated to climate weather? Because we get asked that questions and decisions are not made for us, despite imminent climate change questions. So there is something like this, and I don't know what to say. And it's partly a communication problem that we probably don't explain the value enough, because in the end, the decision is made by people who look at a budget, and they will make a decision against you or for something else, or vice versa. It's like that, And whether you do manned spaceflight, which is a lot more expensive, or you invest in climate change. What's the value for society of one versus the other, and where does your investment go? And I think it's a communication problem in the end, which we haven't mastered yet. So that's why we get asked this question again and again.
Jean-Paul, what's your take on it?
Yeah, I think it's all about communication and telling people what's useful is the supercomputer. I mean, I guess most of us here, are looking at climate, for example, or weather forecast, but we're also interested in discovering new things or even new technological progress. And I think it's a quite broad, communication, science communication aspect that also is important to bring. And of course, a supercomputer is a tool to, to lead these, science discoveries.
Mm-hmm. Yeah, communication, I mean, that's what we did here today. Yes. And I very much enjoyed your talks, and I guess people did so too. This brings me to a closing. Thanks so much for the discussion here and for your insights and your discussions. That was really interesting. And I turn back to Joost.